In this video, we are just going to work through a review sheet for our second exam. So first, we have this question: use implicit differentiation to find the slope of the line tangent to the curve at this point. So first, we need to take the derivative of this function, and the derivative of this function is going to be some product rules. So the first piece is going to be 4 times 3x squared y squared, derivative of the first, times the second, plus derivative of the second, derivative of y squared, 4x cubed, 2y, y prime. The derivative of y squared is going to be 2y, y prime, minus derivative of the first, 5y cubed, minus derivative of the second, 5x times 3y squared y prime, equals the derivative of x is just 1, the derivative of y is y prime. So now we have this long derivative, and we want to solve for the derivative y prime. So we're going to put the y prime terms by themselves. Let's start by simplifying a little bit. 4 times 3 is 12, x squared y squared, plus 4 times 2 is 8, x cubed y prime, minus 5y cubed, minus 15xy squared y prime equals 1 plus y prime. Okay, let's bring all the y prime terms to one side and all the regular terms to the other side. So the regular terms are 12x squared y squared minus 5y cubed. So we did that one, we did that one. And then we have the 1 on the other side, so I'll do a minus 1 because I'm bringing it to the left. And that's equal to y prime, that's that last term, minus 8x cubed y prime plus 15xy squared y prime. And now from here, we see that we have a y prime in all three of our terms on the right. So I'm going to pull that y prime out and divide both sides by it. So in the end, I have 12x squared y squared minus 5y cubed minus 1 all over. That first term, y prime, divided by y prime is just 1. The second term divided by y prime is 8x cubed y. And the third term divided by y prime is 15xy squared. And then on the right, we're left with just y prime. Now we just need to plug in our point, x equals 1, y equals 2. So we have 12 times 1 times 2 squared minus 5 times 2 to the third minus 1 over 1 minus 8 times 1 times 2 plus 15 times 1 times 2 squared equals y prime. And now 12 times 2 times 2, 12 times 4 is going to be 48 minus 5 times 8, which is 40, minus 1 across the top and across the bottom. Across the bottom, we have 1 minus 8 times 2 is 16, plus 15 times 4 is 60, which gives us 48 minus 40 is 8 minus 1 is 7, over 60 minus 10 is 50, minus 6 is 44, plus 1 is 45. So we get 7 over 45, which is answer C. Moving along, number 2 says let f of x equal e to the negative x, then f to the 100th, or the 100th derivative of x, is equal to what? Well, the 100th derivative of x, let's see what this means. So f of x equals e to the negative x. Then f prime of x is going to be equal to, remember, the derivative of e to the x is just e to the x. So the derivative of e to the negative x is going to be the chain rule, derivative of negative x, which is negative 1, times the derivative of e to the x, which is e to the x. And so we keep our e to the negative x, we get a negative 1 sign out front. The second derivative is going to be, we get the same thing, we do the chain rule, we get 2 negatives out front, which makes a positive, which just gives us e to the negative x. If I did the third derivative, I would get another negative sign out front, and the fourth would kill the negative sign. So what we see is odd derivatives give us a negative sign. Even derivatives don't give us a negative sign. This is an even number, which means we don't have a negative sign. Even derivatives don't give us a negative sign, so we have one without a negative sign. And that's all there is to number 2. Number 3 says a ball is thrown straight up from the top of a 100-foot building with an initial velocity of 80 feet per second. Suppose the gravitational constant is g equals negative 32 feet per second squared, and the equation for the position of the projectile is given. At what time does the ball reach its maximal height? So we see that we are throwing the ball straight up from the top of a 100-foot building with an initial velocity of 80 feet per second. If we want to know at what time the ball reaches its maximal height, well, we know that we'll have the maximal height when you throw a ball up into the air and then it comes back down. We have a parabola that's upside down. If we take the derivative, the point where the slope is 0 is going to be exactly where we have that maximal height. So let's take the derivative. Let's say s prime is equal to y0 is a constant, that goes away. v0t just turns to v0 plus 1/2 gravitational constant times 2t. And we have values for our initial velocity and our gravitational constant. So we're going to set our derivative equal to 0. And our initial velocity is 80. 1/2 times 2 is just 1, and our gravitational constant is negative 32. So let's subtract 80 to the other side. We get negative 80 equals negative 32t. We'll divide by negative 32, and I get 80 over 32. Now 32 is 8 times 4. So 80 over 32 is equal to, I can divide by 8. That's an easy one. I can get 10 over 4. I can divide this by 2, and I get 5 halves. 5 halves is the same thing as 2.5, 2.5. So for 3, we just get that it will take 2.5 seconds to reach our maximal height. If we want to know what that maximal height is, we just plug 2.5 in for t in our initial equation, where, of course, we started at the top of the 100-foot building. Notice that starting at the top of the 100-foot building and starting on the ground don't change our answer to this question, but it would change our answer to how high the projectile went. Number 4, we have a 10-foot ladder that's leaning against a wall. The bottom of the ladder is being pulled away from the wall at a constant rate. So here I have a ladder. The bottom is being pulled away at a constant rate of 2 feet per second. And it's a 10-foot ladder, which means we have a 10 on the hypotenuse. Our ladder is 10 long. And the question is, at what rate is the top of the ladder sliding down the wall? So what is this rate here when the bottom is 6 feet from the wall? So when the bottom is 6 feet away from the wall, this is 10 feet. So we have a lot of information here. We have a triangle. We only have really 2 equations for a triangle. We have the area equation, and we have the Pythagorean theorem. The Pythagorean theorem tells us a relationship between all 3 sides. It seems like we're looking at a relationship between the 3 sides, so let's start there. A squared plus b squared equals c squared. Now, if I take the derivative of this, I have to do the implicit differentiation because I don't know what I'm taking the derivative with respect to time. So here I'll get 2a dA dt plus 2b dB dt equals 2c dC dt. And now let's understand what we have here. We have, let's call this A, B, and C. Usually we call the hypotenuse C. And let's see what values we have. Well, we're looking for the rate at which the ladder is sliding down. So we're looking for this dA dt. We don't have A yet. We do have B. We know we're looking at B exactly when we're 6 feet away. And so we have 2a dA dt plus 2. In fact, we have B and dB dt, right? We're sliding away at a rate of 2 feet per second. So this is times 6 times 2 equals. Now think about the change in C. If I have a 10-foot ladder, over time, it's not changing at all. A 10-foot ladder is not changing at all over time. It's staying a 10-foot ladder even if it's falling down. So what that means is my dc dt, my change of C over time, is actually 0. So on the right side, I just get a 0. Now we have a problem. We have two variables in one equation. But I do have two sides of this triangle, and I'm looking for the third side of this triangle to get rid of another variable. So I can use the Pythagorean theorem again. I can say, okay, a squared plus b squared is 6 squared equals c squared, which is 10 squared. And so we get a squared plus 36 equals 100. Subtract 36, a squared equals 64. The square root of 64 is 8. A equals 8. And so we can take this equation, I'm going to bring it back over here, and I'm going to say we have 2 times 8 times dA dt plus 2 times 6 times 2 equals 0. 2 times 6 is 12 times 2 is 24. We have 16 dA dt plus 24 equals 0. Subtract the 24 to the other side. 16 dA dt equals negative 24 divided by 16. dA dt equals negative 24 over 16. We can divide them both by 8, and we get negative 3 over 16 divided by 8 is 2. And so we get negative 3 halves feet per second. Negative 3 halves is an answer. It's letter C, and that's number 4. Number 5 says the graph of the derivative f prime of x is given below. Determine the intervals on which the original function f of x is increasing or decreasing. Remember, f of x is increasing when the derivative is above 0 and decreasing when it's below 0. So this is going to be decreasing from negative 2 to the left. We're going to be increasing between these 2 points here. Then we're going to be decreasing through all of this until we get to here, and then we're increasing again. Number 2 says to find the local mins and maxes. Now, this is a little bit of a tough one because remember, we have the derivative here. This is not the function, this is the derivative. And so the local mins and maxes of f are actually going to be this negative 2, this negative 1, and this 6. This is going to be a min or max. This is going to be a min or max, and so is this. And in fact, if we wanted to really be specific, we could even tell whether it's a min or a max, because, for example, let's look at this point all the way on the right. We are increasing on the left, we're decreasing on the left side of the function, and then we're increasing to the right side of that point, which means our function is going to be at a local minimum at that point. We are decreasing to the left of this one and increasing to the right again, so we have another min. So this is a min, this one's a min, this one's a min. And then for this one, we have increasing on the left, decreasing on the right, which means we're going to be finding a local max. But the question didn't ask for that. Number 6 says find the extreme values of f of x, where f of x is this function. Remember, the extreme values are when we take the derivative and set it equal to 0, but it's also the endpoints of the function if we have a closed function. So f prime of x, the first derivative, is equal to 2x plus 3. And the first derivative is equal to 2x plus 3, which means when we set it equal to 0, we get 2x equals negative 3, or x equals negative 3 halves. And so our extreme values, our possible mins and maxes are 0, 2, negative 3 halves. And now we don't know which one is a min, which one is a max, which one's the global min or max. So let's plug them in. F of 0 is equal to 9. F of 2 is equal to 4 plus 6 plus 9. 4 plus 6 is 10, so this is 19. And f of negative 3 halves is equal to 9 fourths minus 9 halves plus 9. 9/4 minus 9/2, let's make them the same. So let's say this is times 2 times 2. This is 18 over 4. So 9/4 minus 18/4 is going to be negative 9/4. So we have f of negative 3/2 is equal to 9 minus 9/4. And so what we see is this is obviously the global minimum. And this one here is obviously the global maximum. And that's what we get for number 6. Now this one we also have to find the extreme values of f of x equals this other function. F of x equals this other function. Let's take the derivative of it, and we get f prime of x is equal to negative 2x minus 7. If I set this equal to 0, I add 7 to the other side, I divide by negative 2, x equals negative 7 over 2. And so in this case, we have the extreme values, x equals negative 7 over 2, but we also have 0 and 2 again. So if I plug in 0, f of 0, I get 5. If I plug in f of 2, I get negative 4 minus 14. So that's negative 18 plus 5 is going to be negative 13. And then f of negative 7/2. Let's work through this one carefully. Negative 7/2 squared is going to be positive 49 over 4. But we have this extra negative sign, so we're going to tack that on. And then we're going to have negative is a plus 7 times 7/2 is 49/2. So we get something really similar to the previous problem, plus 5. Now, we have f of negative 7/2 equals negative 49/4 plus 49/2 is going to be negative 49/4. So we're going to get 5 minus 49/4. And 49/4, let's just see what this is. This is 5 minus 9. Well, 49 is actually 12 and 1/4. 5 minus 12 and 1/4. And so what we see in this case is 5 minus 12 and 1/4 is not going to be smaller than negative 13, and it's certainly not going to be bigger than 5, which means our extreme value actually doesn't end up being anywhere over this interval of this function. So when we took the derivative and set it equal to 0, this value is not a global max or a min. Here we have this as the max and this as the min. Awesome. For number 7, we have the question, let f of x equal this function. Find the intervals of increasing or decreasing and local minima and maxima. Also find intervals of concavity up and down and inflection points. So let's start by finding the increasing and decreasing intervals as well as local mins and maxes. And the way we do that is we take the derivative of the function. So here f prime of x is going to be, make it bigger for more room, 7 over 7 is just 1, so we get x to the 6th minus 5 over 5 is just 1, x to the 4th. And if that's f prime of x, we see that this is equal to x to the 4th times x squared minus 1. And if I'm setting that equal to 0 to find my points of minimas and maximas, I am going to get x to the 4th could be equal to 0, which means x equals 0. I could also get x squared minus 1, remember we can factor, to be x plus 1, x minus 1. And so we end up with x equals negative 1 and x equals 1. So our 3 points that are possible mins and maxes are x equals 0, 1, and negative 1. Now we need to find whether those intervals are increasing or decreasing. We need to find whether those are local mins or maxes. So let's plug in some values to see whether the derivative is positive or negative between these points. So let's set up, we have negative 1 on a number line, we also have 0, we also have 1, and we're looking at our first derivative here. if I plug in something less than -1, something really, really small, like -10 or -100, obviously -100 is going to be bigger, the -100 to the sixth is going to be bigger than -100 to the fourth, because we're going to get positive numbers in both cases, and the sixth power is higher than the fourth power. So this is going to be a positive. This is going to be increasing to the left. Now if I plug in -1/2, what I'm going to get is this number is going to be, let's say this is 1/2, -1/2. The left number is going to be a lot smaller, because if we do 1/2 to the sixth, we're going to do 1/2 times 1/2 times 1/2 6 times. That is a smaller number than 1/2 times 1/2 times 1/2 times 1/2 4 times. And so between -1 and 0, we're actually going to be decreasing. Between 0 and 1, we could plug in a half instead of -1/2. But if we plug in a half instead of -1/2, notice we get the same thing, because -1/2 to the sixth is equal to 1/2 to the sixth. And so this is actually still going to be decreasing. And then bigger than 1 is going to be increasing again. And that is our areas of increasing and decreasing. We are going to be increasing before -1, increasing after 1, but decreasing between -1 and 1. So we can say increasing from -infinity to -1, unioned with 1 to infinity, and decreasing between -1 and 1. So that's our part A. Part B says find intervals of concave up and concave down, as well as inflection points. To find inflection points, remember we take the second derivative. So f double prime of x is going to be 6x to the fifth minus 4x to the third. And we notice this is equal to x to the third times 6x squared minus 4. And now from here we see that x could be equal to 0, or in this case we have 6x squared minus 4 equals to 0, or add 4 to the other side, 6x squared equals 4, divide by 6, x squared equals 2/3, square root x equals plus or minus the square root of 2/3. And so our inflection points are x equals 0, the square root of 2/3, or the negative square root of 2/3. And so that's our inflection points. And now we need to find our intervals of concavity. So we're going to do another one of these charts. And we're going to look at x equals 0, x equals negative root 2/3, x equals root 2/3. And we're looking at this function f double prime of x. And so I need test points again. I'm going to plug in something really, really small, like -1,000, something really, really low. If I have -1,000, negative something really big, well, I'm going to get something that is very negative, because -1,000 plugged in here is going to be a really big negative number. And it's going to dominate this other number because we have a lower power. And so this is going to be concave down. Now on the other side, we could look at something really, really big as the thing above the square root of 2/3. If I look at something really, really big, like 100 or 1,000, I have a really positive number. So I'm going to be concave up on the right side. Now choosing these intermediate points is a little tough, but I can tell you that -1/2 is between negative root 2/3 and 0, and positive 1/2 is between 0 and 2/3. So we can use the halves. And let's see here. If I plug in positive 1/2, I get something that is 1/2 to the fifth. And over here, I get something that's only 1/2 to the third, which means the thing on the left is going to be smaller. If you take a small number and subtract a big number, you get a negative number. So here we're going to be negative. And then if we do the same logic with the -1/2, but the signs flip, we're actually going to be positive here. And so there are our intervals of concavity, concave up and down. Okay. Number 8 says find two non-negative numbers whose sum is 40. So we have a plus b equals 40. But we need their product, a times b, to be some maximum. We can say that a times b is equal to some product p, and we need that product p to be maximized. Now up here, we have a plus b equals 40. If I solve for a, I can say a equals 40 minus b, and then I can plug that into our equation. I can say this is 40 minus b times b equals p. And then I can multiply this out and get 40b minus b squared equals p. And where I'm going to have a maximum is when the first derivative is equal to 0. So let's take the first derivative and set it equal to 0. We get 40 minus 2b is equal to p is equal to 0 because we're taking the derivative of both sides. Subtract 40 to the other side, we get negative 2b equals negative 40. Divide by negative 2, and b equals positive 20. If b equals 20, a is also going to equal 20. b equals 20, a equals 20. And that's all we need to do for number 8. Number 9 says shake it up. An appliance company that sells high-end blenders has a monthly profit function given by p of x equals negative 0.3 x squared plus 450 x minus 10,500. Where x is the number of blenders sold, A says how many blenders must the company sell to maximize profit? Once again, that is just going to be setting the first derivative equal to 0. Finding the maximum is setting the first derivative equal to 0. Hopefully you see a theme there. So we have p prime of x is equal to negative 0.6x plus 450. Remember, when we take the derivative of a whole number, it just goes to 0. And we're going to set this equal to 0 to find what our maximum is. If I set this equal to 0, I get negative 0.6x equals negative 450. Divide by 0.6. I get x equals negative and negative cancel, 450 over 0.6, or 4,500 over 6. 4,500 divided by 6 is 750. So we get 750 as our number of blenders to sell. Maximum profit is just going to be the maximum profit, the number of blenders to maximize profit, just plugged into the profit function. So we have p of 750 is equal to negative 0.3 750 squared plus 450 times 750 minus 10,500. And don't worry, on a test we are going to have much smaller numbers. If I multiply all of this out, I get 750 times 750 is 5625. So we get negative 16,8750 plus, I think this 3,37500. I'll check this after the video to make sure I did my math right. Minus 10,500. And then if we do this, we get, okay, first one plus the second one is, okay, 14,750. So we made $147,000 off of our 750 blenders. And that is the end of our review sheet.